material begins with the ideal op-amp. So previously we learned about the kind of circuit devices like we've learned about resistors before, and we've also learned about the voltage source, and maybe we've learned about capacitors before. So these are all the circuit devices that we've learned in the past, and these are passive devices. But when sometimes they also we learned about different kinds of active circuit devices. But today we will introduce a new kind of device called the operational amplifier. And the operational amplifier is also called the op-amp. And the circuit symbol for this device is a triangle with a negative sign and a plus sign. Now there are two inputs to this circuit device. We'll call that V1 and V2. So these are the inputs. There are two inputs that go into the op-amp, and the op-amp has an output. We'll call that V3. So these are called the terminal pins on the op-amp. So terminal pins 1 and 2 are the input, and 3 is the output. Now, what the op-amp does is it senses the voltage difference between V1 and V2, and then it amplifies this difference by a large number. So we'll demonstrate that by making this equation. So we'll say what the op-amp does is it sets the output of V3 is equal to a big number, we call that A, multiplied by V2 minus V1. And in this case, we called V3 is called the output. A is called the gain for now. We'll just call that gain. And it's a pretty big number. So maybe we'll talk about 10 to the third, maybe 10 to the fifth, something like that. But it's just a big number. And V2 and V1, these two, these are the inputs. Okay. So for now, we just want to know some basics of how does the op-amp actually works. So we'll just draw the circuit symbol again, and we'll draw the output is V3, and then we'll draw an input at the minus called V1, and we'll draw another input at V2. So how it works is, because you're taking the output is expected that to be a much larger number than our inputs, so you obviously cannot get power from out of nothing. So how the op-amp works is it requires it to receive DC power in order for it to work. So you got to connect it to DC power supplies. In the case of this op-amp, there are two pins actually in addition to the input and output. The top pin, we call it VCC, and the bottom pin, we'll call it VEE. And these are DC power sources. Now, it depends on how the op-amp is made. In this case, the op-amp is made using another kind of device of a type of transistor called the BJT. And when we make BJT circuits, the positive power source on top, we call that VCC, and the negative DC power source, we call that VEE. But you may also see things like VDD or VSS. And VDD and VSS are when we are making the DC power source, but for a different kind of transistor called a MOSFET. Now, we won't talk much about those for now. We'll just learn about the op-amp as a whole. What inside of this triangle is a more advanced topic that we'll learn later. But just for now, just realize that you need power sources in order to power your op-amp, otherwise it will not work properly. So this is probably the first time that we encounter representing this DC power source using this triangle here. So what does that intuitively mean? So this circuit here is the same as what we can do is we'll put the triangle back of the op-amp and the V1 and the V2 and the output V3. And what this arrow of this DC power source indicates is it looks something like this. So we can draw a DC source and we'll call that VCC, and then we'll draw another DC source, we'll call that VEE, and then the junction, the middle, we'll tap it to the ground, and we'll just connect the other DC power source. So now obviously this circuit on the right, it's a lot more complicated to draw. So what we simplify it down to is just to draw these arrows. But it's important to get used to this kind of newer way of representing the two DC power supplies. And we typically do not draw the power supplies. Because it is assumed that they are there. But we should at least know about them because they will place a limitation on the output of V3 is the output. They will, depending on how high or how low these DC power source value is, it will have a limitation on the output. So even though normally we just draw the triangle by itself for this op-amp, but we should at least be aware of the power supplies. So what I mean by that is, ideally, so in the ideal case, the gain that we multiply, so the gain should be infinity, right? However, in the real life, A is limited. The gain is limited to a finite number due to the DC power supplies. So what kind of value that we can expect for A? So we can expect A to be somewhere around 10 to the third. Now, the units is volts over volts. It's a unitless, dimensionless value. What are typical VCC and VEE values? VCC values typically is around 5 volts. VEE is typically around negative 5 volts. So you can expect it to be somewhere around this range. Now let's talk about some terminology. Now, okay, let's just draw it again. So our output is V3, so and input of V1, and V2 is the other input. So remember, V3 is equal to gain times V2 minus V1. So let's talk about some terminology. V3 is called the output. Okay, we call this thing the output terminal of the device because we kind of pretend it has been connected to something else later in the future. So that's the output. And V1, it has negative sign, right? It has a negative sign in front. So what do we call this? Well, the name of V1 is called the inverting terminal. Okay, and V2 has a positive sign in front. So due to obvious reasons, we call that the non-inverting terminal. Okay, so V3 is the output terminal. V1 has a negative sign, so it's the inverting terminal. And V2 has a plus sign, so it is the non-inverting terminal. And for obviously reasons, the V2 lacks the negative sign, so it's non-inverting. Okay. So let's expand on this equation a little bit more. There are two very important aspects of the op-amp is why the op-amp is so powerful. So these two things that we want to learn about, one is called differential gain, and the other one is called common mode rejection. Principle. Okay, so we'll learn about these two things. So to demonstrate this, I'll just give an example. It will make it much more clear if I just give the example. So let's say we have an op-amp and V2 is equal to, we just input V2 with 5 volts. And then we input V1 with 3 volts. Now, as a property of the op-amp, A, we are told A is 10 to the 3. So the question is, what is V3? Okay, so it's very simple to solve this. What we do is we just say V3, just like how the equation is for the ideal op-amp, is A times V2 minus V1. So we were trying to find V3 is equal to 10 to the third multiplied by V2 is 5 minus V1 is 3. 2 times 10,000. So V3 is 20,000 volts on our output. Okay, so it's 10,000 times amplification of the difference of V1 and V2. Okay, so clearly V1 and V2 are different. They're different. One is at 5 volts, the other is 3 volts. So what is that called? When the two inputs are different, we have a name for that. It's called differential input. Okay. And when we have differential input, the result is called differential gain. So there is a gain. In fact, it's a huge number. As you can see, V3 is 20,000. That's the differential gain, is when the V2 and V1, our inputs, are different. It's a huge number. So the output has amplified when V1 and V2 are different. And when V1 and V2 are different, we actually have a name for this. We call this differential input. Now, the opposite case happens. It's very interesting. So let's give another example. Let's say V2 is equal to V1 and they're both equals to 2 volts. We input this to the op amp. And again, A remains the same, it's equal to 10,000. So the question is, what is V3? Okay, so V3 is equal to A times V2 minus V1. So V3 is equal to 10,000 times 2 minus 2, so 0. Yeah, and so then V3 is 0. Okay, so what is the observation? Well, there's no amplification here. So V1 and V2 are the same. Okay, there's actually a name for this. It's called common mode input. And when we have common mode input, when V1 and V2 are the same, there is 0 amplification. So the two signals, the input are the same, it gets rejected. There's no amplification. The name for this is called common mode rejection. So let's summarize this. If V1 and V2 are the same, if our inputs are the same, we call this common mode input. And the consequence is that there is 0 amplification, and we call that common mode rejection. Whereas if V2 and V1 are different, we call that differential input. And there will be an amplification that is huge. That is called differential gain. And as you can see, it can be very, very big. So the conclusion that we draw is we only amplify the differences in signals. And we amplify the differences, but we reject the commonalities. Okay. So this is a very, very powerful these are very powerful principle of the op-amp that we'll investigate a little bit further in a little bit. But for now, I wanted to just give a little bit more terminology before I move on. So our op-amp again, we have our two input nodes, and then we have our output terminal. So we call this an op-amp, and this is called because the output, there are two inputs, but then the output is just one. We call this a single-ended output. And this is the kind of op-amp that we will study in this course. But you should be aware of another kind of op-amp, and it's very, very rarely used in this textbook, but you know, in future courses you will encounter this more. It has the two inputs like before, but then there are two outputs. This is called double-ended output. Now we will not study this in this course, but you should just know that they exist. Okay. Now, the simplest amplifier actually is just the single-ended input and single-ended output. So So it's just like this. And then, okay, let's draw the triangle. And then it just output like this. This is called single ended input and output. I mean, it just takes your input voltage multiplied by some gain. So let's, it just V2 is equal to A times V1, right? It's not, it's very simple. So anyways, in this course, we want to focus on the, two inputs, but one output called single-ended output. We call this differential amplifier. But there are other kind of differential amplifiers, like the double-ended output. But we're not going to study the double one. Now, we should get in the habit of representing this terminology a little bit better. So I'm going to, from now on, I'm going to call this I'm going to redraw the triangle. The output, I'm going to call that V out for obvious reasons. The inverting terminal, we call that V in minus. And the non-inverting terminal, we call it V in plus. So this is the standard terminology that we should get used to using. For the single-ended output op amp, just do V out is equal to A times V in plus minus V in minus, okay? And then for the double-ended output, if you're curious to know how is the relationship between input and output, okay, I'll just briefly explain that right now. So the inputs are the same, but in the case of the double-ended output of the kind of amplifier, is actually there's a two outputs. So one would be V out plus and V out minus, and the relationship would be V out plus minus V out minus is equal to A times V in plus minus V in minus. Now, notice that the plus and minus are flipped on the input and output, and that's because there is a name for this kind of double-ended output of the amplifier. Again, we call it differential amplifier. And one of the famous things that a differential amplifier does is it inverts the output, so it's flip. But this is very advanced topic that we'll study much later. So we just, for this course, we're only interested in studying this single-ended output. So the question is probably at this point is, why do we care about only amplifying differences in signals and then rejecting the commonalities? Like, what is the motivation behind what we're learning all of this is about? So I'm just going to give one example. There are many reasons why we would be interested in studying op amps, but for now we're just going to learn about this the most very intuitive and a very, very powerful application of this. So I'm going to talk about this two-ended differential op amp, a differential amplifier. So let's talk about a problem that might arise. Imagine you have a clock. A clock signal. Now, if you know anything about a clock signal, and on the computer, the clock signal looks like a square wave. And let's say you run the clock signal through a long wire, and then on the output will produce your clock signal. Now, let's say that you did this and you nearby you had an information signal. Maybe it could be anything. It could be like carrying data, or it doesn't matter. And you decided to run this information signal to your output, and you would expect it, your information signal, some sine wave. You expect the output to be, some sine wave. But the thing is, if you ran this information signal wire very close to the clock signal wire, because it's in close proximity to each other, there will be these parasitics, and there will also be these noise capacitance. The name for this is actually called line to line capacitance. So the consequence of this is your output for the information signal, after traveling through a very long wire next to the clock line, because the two wires are in close proximity to each other, the clock signal of this square wave, it will actually impart itself in a small component. It will impart itself onto the information signal. So you will get some, thanks to due to this problem of this capacitors, it will have some like clipping on the clock signal imparted onto your information signal. So a tiny bit of this clock signal imparts itself on the information signal, and this is called noise. And this is very bad because it distorts the information signal. So this is obviously as a problem. So how do we resolve this problem? The solution is actually very innovative. What we can do is we can take our information signal and we run it through, we split it up into two equal but opposite components. So one component, it looks like this, and the other component looks like this, equal but opposite. Now we run this two signals in two wires to the output. Okay, let me draw everything much smaller so that we can fit everything. So you take your information signal, you split it up into two equal but opposite signals, you run it through two very long wires, and then you get your output on the other side. Okay, then you run your clock signal down the middle. You run your clock wire down the middle. There will still be line to line capacitances. There will still be line to line capacitances, and the output will still be clipped so you have your square wave, and it will still have some clipping. It's equal and opposite, right? So it's some clipping. It will, again, the clock signal will still impart itself on these two outputs as well. But the important thing is that when you recombine your clock signal there's a way you can actually convert this two-ended output back into combined together to one signal. And when you do that, the noise will, yes, the clock signal did create noise in the two equal and opposite signals, but because it pulls on it in equal and opposite, when you recombine the two signals together on your output, the noise cancels out. And why is because the noise caused by the clock is producing what is common in both signals. And so because it's common, through the common mode rejection principle, as we talked about earlier, it rejects the commonality components, then the end result is this op amp will help us be able to, this differential amplifier will help us be able to not have any noise on the output. It's immune to noise. So this is a very powerful application for this differential amplifier. So now we understand the motivation of why we are interested in studying differential signals. But obviously, we must start with the basics and first talk about the single-ended output before we move on to this more complicated circuit. So, as we have talked about earlier, the op amp amplifies the difference, but it removes all the commonalities. So we'll talk about what's called a differential input signal. So assuming that we put the input V1 and V2 go in there and the output's V out. So there is a name for the component that's different, V1 and V2, the component that's different, there is a name for that. It's called V in D. It's called a differential input signal, and it's equal to V in 2 minus V in 1. It is simply just the difference. It's just the difference. That's all it is. That's all it is. And meanwhile, what if V1? So what if V1 is equal to V2? In this case, okay, what if V in 1 is equal to V in 2? Okay, in this case, V in, just the average, is just taking the average of V in 1 minus V in 2. It's just the average, right? So the name for this is called the common mode input signal. There's a name for that, V in CM, common mode. It's equal to 1/2. This is just taking the average of the two. So the differential input signal is taking the difference of V in 1 and V in 2, but the common mode input signal is taking the average of, it's taking what's common to both. It's taking what exists in both, what is the same in both, so it's just taking the average. We call that common mode input signal. Now, in the textbook, the differential input signal is called equation 2.1, and the common mode input signal is called equation 2.2. What you can do is, if you combine equation 2.1 combine that with 2.2, you can get two different, you can write the V in 1 and V in 2 in terms of the common mode and differential signal. So you can do some just algebra and solve for V in 1, V in 2, and it's equal to V in common mode minus V in differential divided by 2, and V in 2 is equal to V in common mode, not minus this time, is plus V in differential over 2. And I recommend you just solve this on your own. You just do it once and then you will understand it a little bit better. So yeah, so please go do that on your own. But so why would I even try to show you these two equations? The reason is because we can give it a pictorial representation of these two equations. So imagine we have V in D, and then we have V in D again, but the difference is one is put the minus sign on top, the other is putting the minus sign at the bottom. Yeah, let's put this like this, and then let's put a DC source, and this is V in common okay, this is V in common mode, and then we can draw V in 1 at top, and then we can draw V in 2 at the bottom. Right, and actually yeah, so as you can see, let me just reverse it. Yeah, okay, this makes more sense because there's a positive sign in front of V in you know, as you can look, if you look, you know, Vn2 has the positive sign, right? So Vn2 is higher, so you're going up voltage, so Vn2 is higher. Meanwhile, Vn1's lower, right? So because Vn1 has the negative sign in front, it has this negative sign here. So yeah, okay, so this is the pictorial representation. Now, I drew it in such a way that V in CM is the DC and V in D is AC, right? Okay, it doesn't have to be necessarily this way. You should note that CM doesn't necessarily have to be DC, but it usually is, because usually the common component is a DC biasing, DC voltage shift. But it doesn't necessarily have to be. It could be, you know, AC as well, but usually the common mode part is DC. And likewise, V in D does not need to be AC signal, but usually it is AC signal. So just note that. Let's talk about the characteristics of an ideal op amp. Okay. So the ideal op amp has several assumptions that we make, and we make these assumptions, so that is the ideal. The first is that we have infinite input impedance. So what does this mean? I will draw a very large op amp triangle on the right. Okay, and our input is 1 goes here, it has the positive sign, and then 2 it goes here and like has negative, just as before. What we mean by infinite input impedance is that it's an open circuit between 1 and 2. Open circuit means that R in is equal to infinity, right? So if R in is infinity, or the open circuit, then the current going in 1 is equal to 0. There's no current going there, and likewise there's no current also coming out of it either. Both is 0. So what does this mean? Infinite input impedance means that Rin is infinity such that I1 is equal to I2 is 0. There's no current go into the input of the op-amp. The next assumption of a characteristic of an ideal op-amp is called zero output impedance. So what does this mean? It means that R out is equal to 0. So if we have the output of the op-amp is 3, terminal number 3, then so how does this represent of this op-amp? Okay, there is we'll just demonstrate something really fast. Okay. So what an op-amp is like VA, there's a voltage control voltage source which is equal to A multiplied by V2 minus V1, that's equal to V3, right? So the meaning of here is number 2, a zero output impedance is that the connection to this ground below the voltage control voltage source is R out equals 0, right? Zero output impedance. So this op-amp is kind of like the example circuit equivalent of what happens in an ideal op-amp. What's inside of this triangle if it was ideal. Now there's another assumption that we need to make if it's an ideal op-amp. Ideal op-amps, they have what's called zero common mode gain. The meaning of that is zero common mode gain. It also means infinite common mode So what that means is, as we have learned earlier in the examples that I gave, when the two inputs are the same, there is no amplification. It is called common mode rejection because we reject the components of the signals of the input signal that is common to V1 and V2. So in this case here, in the ideal op-amp, it really does produce 0. Any commonalities of the input signals, it really does produce 0 in the ideal op-amp. Later we will study the real practical op-amp and we will understand why it may not be zero common mode gain, also called infinite common mode rejection, why it may not perfectly cancel out the commonalities. But for now, just know that when the two inputs are the same, the output is perfectly at 0. The fourth assumption for an ideal op-amp, it says that there is infinite number of open loop gain. So this is self-explanatory, is that A is equal to infinity. Actually, now we will talk about the name for A, the amplification. We have a name for this, is called open loop gain. Why is open loop? We'll explain that in a little bit, but for now we have a name for this. A is called open loop gain, and in ideal op-amp it is infinity. Obviously in the real op-amp this is limited by the power source and other circuit considerations, so it will not be infinity, but for now we take it as infinity. There's one more thing about the ideal op-amp, number 5, is called infinite bandwidth. Infinite bandwidth means it works for all frequencies. This is not the case for the real op-amp. It's limited bandwidth. It does not work at all frequency, especially up to very high frequency. The circuit performance gets degraded. But for now, we're studying the ideal op-amp. It works for all frequencies. Okay, so we will just conclude with just a couple of example practice problems, and these are very easy. After this video, the component in this gets much more complicated and difficult. The course gets more difficult, but this is just the introduction, so these practice problems are very, very easy starting off. So we'll do example problem number 2.2. So in 2.2a of the textbook, it says we are given an op-amp that has the open loop gain is equal to 10 to the third. We are given this op-amp. And we are also told that V2 is equal to 0 volts. V3 is equal to 2 volts. We are asked to find out what is V1. Okay, so by now you should probably recognize the symbol. I'll draw it one last time. But you probably know it by now, but I'll draw it one last time. And again, I'll write out the equation. It is V3, in the ideal op-amp, V3 is equal to A times V2 minus V1. So we'll just do 2 is equal to 10 to the third. 0, V2 is 0, and V1, we're solving for that. Okay. So 2 is equal to negative 10,000 V1, right? And okay, so 2 divided by negative 10,000, that is equal to negative 2 negative 2 times 10 to the negative 3. Okay, so okay, let's write that. So V1 is equal to negative 2 times 10 to the negative 3 is millivolts, negative 2 millivolts. Okay. Problem number B is also pretty simple. I forgot to say that actually question 2.2a asks for 2 more things. It asks for what is V in D. What is that? Again, V in D, if you remember, is equal to V2 minus V1. Remember from here, V and D, the differential input signal is V2 minus V1. It's just the difference. So V2, as we found, we told is 0, but V1 is negative 2 millivolts. So V in D is equal to 2 millivolts. Okay, and the next question is, what is V in Cm? What is that? So if you recall from the previous equation, we said that the common mode input signal V in Cm is equal to 1/2 times V1 minus V2. It's just the average, right? So let's just do that. So V in Cm is equal to 1/2 times V2 plus V1, just taking average. So we just say, okay, so it's 1/2 times V2 is 0 plus V1, as we found, was negative 2 millivolts. So V in, see, it's just the average. V in CM, the common mode input, is negative 1 millivolts. Okay, now let's find 2.2b. Let's go to the next question. We are told that V2 is equal to 5 volts and V3 is equal to negative 10 volts. We're going to use the same A open loop gain from before, and the question is, what is V1, V in D, and V in CM? Okay, we're doing the same problem as last time. So V3, remember V3 is equal to A times V2 minus V1. So we will just say negative 10 is equal to A is 10,000 from the previous, yes, so A is 10,000 times 5, V2 is 5 minus V1. So okay, so let's just do that. So A is 10 A is actually not. So A, we're going to reuse A from before. It's just 10 to the 3, so which is E to the 3, 10 to the 3. I'm sorry. Yeah, okay, this is the one. We're using the same A from before. Okay, so we solve for V1. Okay, so minus 5 both sides times negative 1. So V1 is equal to negative 5 minus 10 E3, 10, okay, divided by 1000 is equal to then you multiply by negative 1. Yeah, okay, so V1 is equal to 5 plus 10 to the 10 divided by so divided by 1000 is 0.01. So V1 is equal to 5.01 volts. Okay, let's find VD. Remember, it's just the difference of the two inputs. So okay, so we just do V2 is 5 minus 5.01. V in difference is negative 0.01 volts. Okay, and V in common mode, remember it's just the average, so we take 1/2 times V2 plus V1. So V2 is 5 plus V1 is 5.01. Okay, so now we have 10.01 divided by 2. So that's 10 over 2 plus 0.01 over 2. So that is 5 plus 0.005. So V in CM is equal to 5.005 volts. Okay, let's do another practice problem. Let's do 2.2c. Yeah, we're going to do all the practice problem, but now it's 2.2c. We're told that V1 is equal to 1.002 volts, and we are told that V2 is equal to 0.998 volts. I assume we are going to reuse the same A. A is just A is 10 to the third, 1000. So 10 to the third. So we're asked to find out what is, well, we're trying to find the one that's not the last pin. It would be V3. Yeah, what is V3? And also find out what is, again, like same procedure as before, V in D differential input, and also find out what is V in CM common mode input. Okay, so yeah, let's do that. So again, V3 is equal to A, which is 10 to the third times V2 minus V1. So 0.998 minus 1.002. Okay, so V3 is equal to 1000 times yeah, so it's well, it's 4 0.004. Yeah, so then V3 is equal to, well, I think, it's negative 0.04, so V3 is equal to negative 4 volts. Okay, and V in D is equal to just the difference, V2 minus V1. So V2 is 0.998 and V1 is 1.002. So we just solved that just now. It was negative 0.004. So we can say that negative V, so we can say the differential input is equal to negative 4 millivolts. Okay, yeah, okay, and V in common mode is equal to the average of the two inputs, remember, so it's a V1 plus V2. It would be 0.998 plus let's remain consistent. Let's say it's 1.002 plus 0.998. Okay, so that there is that 2 adds to here, then that becomes 1 plus 1 is 2. Okay, so V in CM is equal to 1/2 times 1 plus 1 is 2, so then the V in CM is equal to 1 volt. So common mode input is 1 volt. Okay, last practice problem from 2.2, 2.2D. We are told that V1 is equal to negative 3.6. We are told that V3 is equal to negative 3.6 volts. Okay, so again we're finding whatever terminal pin is not here, so that is V2, and we're also finding same procedure as before, V and D, and also we are trying to find in VN common mode. So we're trying to find these things. So how we can do this is we can say V3 is equal to A times, okay, so negative 3.6 is equal to A, which is just 1000. We're using A from before, so it's 1000 times V2 minus V1. So V2 minus, which we're trying to find, minus V1. So divided by 1000 is equal to V2 plus 3.6. So V2 is equal to negative 3.6 times negative divided by negative 3.6 divided by 1000 minus 3.6. Okay, so what we can do is yeah, it's going to be okay, we're gonna have to do it like this. So it's 3.6 plus this is just finding the magnitude first. 0. Uh, 1 2 3, so it's 0 0 3 6 1, yeah, okay, so then that is 63063, like that. Okay, okay, okay. So then v2 is equal to negative 3 point 6036, yeah, the volts. And now we're finding v in the difference. Okay, so we just found that here it was oh, but yeah, okay, times, yes, okay, let's find the difference. So it's just v2 minus v1. Okay, so it's negative 3.6036. It's just a minus the difference, right? So minus 3.6 v2 minus v1. Oh, okay. Yeah, okay, so let's do it this way. So we can say 6. Okay, I need more space because it's which is minus 3.6. Oh, okay, okay, so it's 63000. Okay, that's 3 point. I think I okay, okay, it's the difference. V1 minus v2, negative 3.36036 minus negative 3.6 is just that minus 3.6, so it should just be finding the magnitude would be 3.6036 minus 3.6. Yeah, okay, yeah, okay, okay, so so then you put them, we have to put 9, so v in d is equal to somewhere just negative, oh, this is 0, yeah, okay, it's just say negative 3.6 millivolts. Yeah, okay, and finally let's do v in common mode is equal to, we just take average of vn1 and vn2, so vn1 is negative 3.6 volts and vn2 is negative 3.6036 here. Yeah, okay, so yeah, let's find the magnitude plus 3.6036. 60 12 7.2036 negative, because there's mine. Okay, yeah, but and then we just have to divide by 2. Yeah, okay, so vn cm, don't forget the minus sign, so it's negative 3.6018 volts. So this concludes the section 2.1, which is actually very simple. The course material moving on from this point will be a lot more complicated. So it gets progressively a little bit harder, but it's still, the textbook still goes through and explains things really, really well. So this concludes the section 2.1.